Imagine standing in the ancient Mediterranean, turning one small handle, and watching a machine point to a future eclipse. No electricity, no telescope, no digital display, only bronze teeth carrying astronomical cycles from one dial to another. The Antikythera mechanism is often called the world's first analog computer. That title is useful, but it can also hide the real mystery. The machine did not appear by magic, and it was not impossible technology. What makes it extraordinary is that enough of it survived for us to see how much ancient engineering the historical record failed to preserve. Its story begins with a Roman-era shipwreck near the Greek island of Antikythera. Sponge divers found the wreck in 1900, and the recovery continued into 1901. Among statues, coins, and cargo was a corroded mass that looked far less impressive than the sculptures around it. Only after the material began to separate did observers recognize bronze gear teeth inside. The ship probably sank in the 1st century BCE, while research places the mechanism's construction earlier in the Hellenistic world. A precision astronomical instrument had crossed the sea as cargo, then spent roughly 2 millennia compressed and corroding underwater. Today, the original survives as 82 fragments. Researchers estimate that only about 1/3 of the mechanism remains, including 30 corroded bronze gears. That means every reconstruction begins with absence. Shafts are broken. Plates are missing. Many teeth have vanished. Yet the surviving fragments preserve bearings, pillars, gear traces, scale divisions, and thousands of tiny inscription characters. The challenge is not simply to make a machine that can imitate the sky. It is to build a model that fits the surviving spaces, tooth counts, inscriptions, and mechanical marks without quietly inventing convenient parts that the evidence cannot support. The core idea is beautifully mechanical. When one gear drives another, the ratio of their tooth counts changes speed and direction. Link enough carefully chosen ratios, and one input rotation can represent several astronomical cycles at once. The mechanism did not calculate with written numerals. Its moving parts embodied the arithmetic. A user advanced the date, and the gear trains moved pointers across calendars and astronomical scales. The bronze did not know why the moon changes phase or why eclipses repeat. It reproduced mathematical relationships that generations of observers had already measured in the sky. The front of the mechanism remains the most debated part because so little survives. Evidence supports displays connected to the zodiac, calendar, sun, and moon. Inscriptions also describe the 5 planets known in antiquity. A 2021 UCL team proposed a compact gearing system that could display that ancient Greek cosmos inside the available space. It is a serious evidence-based model, not a recovered blueprint. This distinction matters. We can show how the proposed rings and pointers may have worked, but we must not present every missing planetary gear as if archaeologists pulled it intact from the wreck. One surviving mechanism reveals how sophisticated the design could be. The moon does not move across the sky at a perfectly constant apparent speed. The machine represented that variation with a pin-and slot arrangement inside rotating gears. As the parts turned, the pin shifted through the slot and changed the output speed. This was not decoration. It converted a simplified model of lunar motion into visible mechanical behavior. A small assembly of bronze parts could make the lunar pointer accelerate and slow, while also helping display the moon's phase. On the back, one large spiral dial organized a 19-year calendar cycle. 19 solar years are close to 235 lunar months, a relationship called the Metonic cycle. The mechanism arranged those months across a 5-turn spiral. Instead of forcing lunar months and solar years into a simple grid, it encoded the mismatch and the repeating correction. The calendar was therefore not a passive list of dates. It was an operating model that linked human timekeeping to repeated motions of the sun and moon. A second spiral handled eclipses. Its 223 lunar months represented the Saros cycle, after which eclipse patterns repeat with important shifts. Glyphs on the dial marked eclipse possibilities and recorded characteristics such as whether the event was solar or lunar and the expected time. Turn the mechanism to a future month, and the pointer could land on one of those warnings. It was not seeing the future. It was carrying a long astronomical cycle forward through gears, scales, and inscriptions. The designers also accounted for a problem hidden inside the Saros. The cycle is not a whole number of days, so a similar eclipse returns roughly 8 hours later in the day. A smaller Exeligmos dial tracked 3 Saros cycles and indicated the necessary time correction. This is the machine's deeper achievement. It did not merely repeat one famous number. It combined cycles and corrections, allowing the user to interpret what the main pointer meant. The result was a compact mechanical interface to a layered astronomical model. Another small dial connected cosmic cycles to public life. Research published in 2008 identified a 4-year display for the cycle of major Panhellenic Games. The same object that organized lunar months and eclipse warnings could also help track recurring human events. That combination makes sense in its own culture. Astronomy, calendars, festivals, and civic schedules were not separate apps. They were different uses of ordered time, brought together inside one case. The inscriptions were crucial because they acted like an embedded manual. Many characters are less than 2 millimeters high, and large sections are hidden inside corroded layers. The surviving text labels scales, names cycles, and describes displays. It also sets limits on reconstruction. A proposed mechanism should not only turn, it should produce the motions the inscriptions say the user could see. Each newly read word can eliminate one attractive but unsupported mechanical solution. In 2005, researchers used microfocus X-ray computed tomography and advanced surface imaging to look through the fragments. The scans revealed internal gear details and text that had been unreadable for about 2,000 years. This changed the investigation. Earlier scholars could study exposed teeth and shadows on the surface. The new data let teams examine buried layers and reconstruct the rear dials with far stronger constraints. Modern imaging did not solve the machine automatically. It supplied evidence detailed enough for historians, astronomers, engineers, and epigraphers to argue with the same physical record. The proposed front cosmos shows why debate continues. Planetary motion seen from Earth includes apparent reversals, so a compact display needs more than simple concentric wheels turning at constant rates. The 2021 model uses epicyclic gear trains and period relationships drawn from the inscriptions to fit sun, moon, and planetary indications into limited space. The model explains many surviving clues, but the authors themselves describe the need to prove whether the full design can be built with ancient techniques. A reconstruction can be brilliant and still remain a testable reconstruction. Could Hellenistic craftspeople actually make it? The surviving teeth, shafts, inscriptions, and fitted components prove that they made at least the preserved mechanism. The difficult question is how widely such skill existed. Precision did not require modern factories, but it did require measurement, patient handwork, astronomical knowledge, and a design tradition capable of turning ratios into hardware. The mechanism is evidence of that tradition. It is not evidence that every ancient workshop could produce the same object. Then comes the tempting question, why did this technology disappear? The safest answer is that the surviving record is incomplete. Ancient texts mention mechanical models, but no continuous chain of comparable geared astronomical computers survives into later centuries. Bronze was reusable, delicate instruments could be broken, and one shipwreck is an accidental archive. We can describe the gap. We cannot identify one dramatic day when the knowledge was erased. History often preserves stone monuments better than the small machines that explain the sky. The Antikythera mechanism should not exist only if we mistake missing evidence for missing ability. Its gears joined calendars, lunar motion, eclipse cycles, public games, and perhaps a complete planetary display in one hand-powered instrument. The machine still contains uncertainties, and those uncertainties make it more interesting, not less. It shows what ancient engineers could build, what modern imaging can recover, and how carefully we must separate surviving mechanism from elegant reconstruction. The real wonder is not that it breaks history. It is that one broken machine makes history larger.